Here we have a summary of the registers. There are two basic ways in which information can be entered into the registers or could be taken out from the registers, the parallel and serial. When we say that we have the parallel way of providing the data into the register, it means that we are providing data for each bit position, for each cell of the register. And at the rising edge of the clock, the content of the register will be updated for all cells at the same time. In terms of the parallel out, we mean that we have access to all bit positions, therefore we can take the data out at the same time again. But when we have the serial way, it means that we can provide the data into the flip-flop, which is the first cell of the register. So at each clock pulse, only one bit of information could be inserted into the register. And similarly for the serial out, we can take out one bit of information at each rising edge of the clock. Okay? If you combine the serial and parallel way of providing the data and taking the data from the registers, we will have four possible options. Serial in, serial out is when we provide the data in serial and we take the data in serial from the register. Then we can have the serial in, parallel out. For serial in, parallel out, data will be provided in serial, but we will have access to all bits of the register. When we have the parallel in, parallel out, we will have this case. So this is parallel in and parallel out. And then we can have parallel in, serial out. When we have the parallel in, serial out, data is provided for each bit position. So the content of the register could be updated at once for all bit positions, but we will have access to one bit of the data at each clock pulse. Over here you can see the structure, the internal structure of a serial in, serial out unidirectional shift register, which is a simple one. As you can see, we have the serial in, therefore the serial data in line is shown here, and we have the serial data out. So at each clock pulse, at each rising edge of the clock, we will provide one bit of information to the shift register, and we will take one bit of the information out of the shift register. And you can see that internally, the output of the first flip-flop is connected to the input of the second one, output of second one to the input of the third one, and output of the third one to the input of the fourth one. And they all are receiving the same clock. So in this way, we will have shifting of the data in this way at each rising edge of the clock. So that's why it is called the unidirectional shift register. We don't have the shifting of the data in the other way. This is not provided for now. The next shift register is similar, but it can give us all the data from the shift register in parallel as well. We have access to the output of each flip-flop directly, and therefore we will have the parallel out option. But still we have the serial input to the shift register, and we have the unidirectional shift register, because the shifting again will be done in one way only. It's unidirectional. Then over here we have the parallel out and parallel in unidirectional shift register. It's still unidirectional, again meaning that we will have the shifting from one side towards the other, from left towards the right. We have the parallel in, we will see how that works, and parallel out means that we have access to the output of the flip-flops directly. In order to have the parallel in, we are going to use this load signal. So with the load signal, we control whether to load the shift register with some value or whether to have the shifting of the data. Let's see what happens when we have load equal to 0. When load is equal to 0, over here we'll have 0, and as the output of the inverter we'll have 1. Therefore, output of the first AND gates will be equal to 0. The output of the second AND gates will be equal to IA in this case, IB, IC, and ID, and therefore the input to the flip-flops will be also similar. IA, IB here, IC here, and ID over here. So you can see that when load is equal to 0, at the rising edge of the clock, the content of the shift register will be updated with the new value which comes from the parallel data in. On the other hand, we can have the load equal to 1. When load is equal to 1, let us see what happens here. When load is equal to 1, we will have 1 here, 0 from the output of the inverter. Therefore, the output from the second AND gate will be equal to 0 for all cases. The output from the first AND gate for the first stage will be equal to 1 and serial in. Therefore, here we will have SI, serial in. The input to the flip-flop to the first one will be equal to SI. For the second stage, we will have 1 here and QA here. Therefore, QA will appear here. And the input to the flip-flop will be equal to QA. For the next bit positions, we will have QB and QC. Therefore, at the next rising edge of the clock, the content of the flip-flops will be updated in this way. The first one will receive data from outside, from the serial in. The second one will receive it from the first one. Third one will receive it from the second one, and so on and so forth. So shifting will happen in this case. Shifting towards the right by 1 bit position. These are two options that we have for this configuration. Then we can have a look at the next more complete, let's say, design. We have the universal shift register. It's universal. It means that we don't have shifting only in one direction, but in both directions we are able to do it. In general, there are 4 operations to be done. The first one is holding the data, second one is shifting towards the right, then shifting towards the left, and then parallel load. In order to control these 4 operations, multiplexers are used, as you can see them here. So for each bit position, we are using 4-to-1 line multiplexer. They receive 4 inputs and they have 1 output, and they are also controlled using these 2 select lines, S1 and S0. So based on the values of S1 and S0, one operation will be performed. We can check them one by one. When we have 0, 0 for S1 and S0, let us see what happens. When S1, S0 is equal to 0, 0, the first input to the multiplexers are selected, I0, and they are provided at the output of the multiplexer. But let us see where they are connected. So I0 for the first multiplexer is connected to the output of the first flip-flop. For the second one, it is connected to the output of the second flip-flop. For the third one, it's connected to the output of the third one, and for the last one, it is connected to the output of the last one. Therefore, when we have 0, 0 for S1 and S0, the input to the flip-flops will be equal to QA, QB, QC, and QD, and therefore in the rising edge of the clock, the flip-flops will be updated by their own value, and therefore they will hold the same value, and the shift register as a whole will keep its current value. Then we have the next case when we have 0, 1 for S1 and S0. In this case, the second input to the flip-flop will be selected. The second input to the flip-flop, we can see that for the first multiplexer, it is connected to the SIR, serial input for shift right. For the second one, it is connected to the output of the first one. For the third one, it's connected to the output of the second one, and for the last one, it is connected to the output of the third one. And then this information will be provided at the input of the flip-flops. So now you should see what happens. Yeah? At the rising edge of the clock, the serial input SIR will be provided here at the input of the first flip-flop. Then we have QA here, QB here, and QC here. Therefore, we will have shifting of the data from left towards the right. So we have shift towards the right. In the next one, we have 1, 0 for the S1, S0. The third input to the flip-flops will be, to the multiplexers will be selected. So we have it here. Let us see where they are connected and where do they receive the data. You can see that for the last one, it receives data from SIL, shift towards the left. For the third one, it receives